In this segment of the AZ-104 course, attention centers on virtual network peering as an integral component within the module on implementing and managing virtual networking. Building on prior knowledge of creating and configuring virtual networks and subnets, this topic delves into how peering links these networks, permitting seamless communication. The objective is to examine core principles behind VNet peering while emphasizing its significance in resource connectivity. Understanding how peering complements earlier steps in network creation will foster a solid foundation for advanced cross-network implementations. The scope encompasses setup processes, configurations, best practices, and considerations for effective peering strategies. Before exploring peering, recall that an Azure Virtual Network, VNet, serves as the backbone for resource communication in the cloud. Each VNet contains subnets for segmenting traffic flows and managing address allocation. Previously covered practices include planning IP address spaces to avoid overlap and employing network security groups to filter traffic. These elements ensure that resources are logically organized and protected. VNet peering maintains these core principles but extends them across multiple VNets, enabling direct communications without a gateway. This context is critical to appreciate how peering facilitates a scalable, efficient, and secure network environment in Azure. VNet peering joins two or more Azure virtual networks, allowing resources to communicate as if they were on the same network. This connection is low latency and uses Azure's internal backbone for data transfer, providing cost-effective and efficient routes. Peering removes the need for complex routing or on-premises gateways by handling traffic between peered VNets within the Azure infrastructure. While subnets belong to individual VNets, peering seamlessly interconnects those networks, making remote services and applications appear reachable through private IP addresses. This concept aligns with modern cloud architectures seeking flexible designs to span workloads across various virtual networks. VNet peering offers multiple advantages. First, it lowers latency by routing traffic through Azure's private backbone instead of external tunnels. Second, it simplifies topology. Peering adds east-west traffic flows for services spread across different networks without requiring VPN gateways or public endpoints. Third, it reduces complexity in multi-region designs where resources must interoperate but reside in distinct VNets. Furthermore, database replication scenarios, microservices, and failover configurations benefit from direct communication. These use cases exemplify how peering supports both high-performance standards and robust security. As cloud-based applications scale, peering becomes central to streamlining network connectivity and management. Before creating a peering connection, careful planning is essential. First, ensure there is no overlapping address space between the VNets. Otherwise, packets cannot be properly routed. Each VNet should have a unique range of private IP addresses to avoid conflicts. Second, confirm that you possess the correct permissions in Azure, typically network contributor or owner, to manage peering settings. Additionally, determine whether gateways or route tables will be used, as certain peering functionalities like gateway transit must be configured. Outlining these considerations in advance avoids disruptions and supports a smooth configuration process for linking virtual networks effectively. Basic VNet peering involves linking two VNets in the same subscription and region. In the Azure portal, you access one VNet, choose peerings, and create a new peering. You specify a name, reference the remote VNet, and set the traffic flow options, such as allow forwarded traffic if routing from a virtual appliance is needed. In parallel, you must configure the opposite side of the peering unless you activate the Use Remote Gateway setting. Once both links are established, the networks are peered and resources can communicate through private IP addresses. This procedure forms the foundation of more advanced scenarios. To use the Azure portal for peering setup, navigate to the Virtual Network blade for the source VNet. Select Peerings and then add. Provide a descriptive name to keep configurations trackable and specify the subscription and virtual network for pairing. Under Configuration, Decide whether to allow traffic from the remote VNet to flow back, typically selected if bidirectional communication is necessary. Enable or disable gateway transit according to design requirements. After saving, replicate the process in the remote VNet if you opted for manual configuration. Post-creation, you can validate connectivity by pinging or using Azure Network Watcher tools. Azure CLI offers a script-driven approach to peering. Here is a simplified snippet. Bash AZ network VNet peering create / name peering autob / resource group RG1 / VNet name VNet A / remote VNet / subscriptions / ID / resource groups / RG2 / providers / Microsoft network / virtual networks / VNet B / allow VNet access. In this command, allow VNet access enables traffic between the VNets. A similar command must be run from the perspective of VNet B, unless you rely on certain defaults or advanced settings. Command line automation is particularly helpful for consistent deployment across multiple environments or when integrating peering into infrastructure as code solutions. Cross-subscription peering becomes useful when different departments or teams within an organization maintain separate billing structures under distinct subscriptions. As long as both subscriptions belong to the same Azure Active Directory tenant, you can peer the VNets. The procedure mirrors basic peering steps, but requires selecting the correct subscription and resource group. Network admins need contributor rights in both subscriptions to authorize changes. This approach promotes collaboration by linking networks that must share data or services while preserving financial boundaries. Such flexible options address organizational complexities without compromising the simplicity of peering-based connectivity. In some cases, networks reside in different tenants altogether, requiring cross-tenant peering. This scenario is commonly found in mergers, acquisitions, or multi-tenant environments. Administrators coordinate to establish the necessary role assignments and allow external access to each VNet. Once permissions are granted, the peering process is similar to cross-subscription. However, careful scrutiny of security and governance is vital. Each tenant might apply unique policies or compliance requirements, so peering connections must respect these constraints. Despite added complexity, cross-tenant peering preserves performance benefits by leveraging Azure's backbone, making it a dependable solution for inter-tenant integration. Gateway transit permits one VNet's gateway to handle traffic for another peered VNet. This is helpful in situations where only one network possesses a VPN or ExpressRoute gateway, but other networks need to route traffic to on-premises resources or external services. The peering configuration includes an option to allow gateway transit, and the peered network can use remote gateway. This approach streamlines costs by sharing a gateway among multiple VNets. However, only one gateway is typically viable in a peering relationship. Understanding these limitations and precisely defining routes ensures robust connectivity for distributed environments. When VNets are peered, default routing sends packets directly across Microsoft's internal backbone. Each VNet retains its IP address space, and traffic is routed without NAT or public exposure. Nonetheless, if advanced routing through a network virtual appliance (NVA) is required, the Allow Forwarded Traffic option must be enabled. This capability lets custom routing or firewall solutions process traffic. Proper IP allocation planning remains critical to avoid overlaps. Disjoint address ranges facilitate efficient route advertisement. Combined with gateway transit, these routing practices streamline complex networks, linking resources with minimal latency or overhead across peered connections. Network security groups, NSGs, filter incoming or outgoing traffic at the subnet or NIC level. In peered VNets, NSGs still function on their assigned subnets and resources. For instance, if traffic from one VNet is blocked by an NSG rule, peering will not bypass that restriction. Administrators must intentionally configure inbound and outbound rules, ensuring that only legitimate flows are allowed. This approach isolates applications at scale while still benefiting from direct inter-network routing. Implementation of NSGs can be extended with service tags or application security groups, creating a layered security model that pairs effectively with VNet peering. Service chaining involves routing traffic from one VNet to another through a set of network services, often security appliances or load balancers. VNet peering enables this by controlling traffic flows in a structured manner. For instance, a common pattern routes traffic from a web tier in VNet A through a firewall or intrusion detection system in VNet B before reaching a database tier in VNet C. Each VNet can be peered with the next, and transfer rules define how packets traverse. Although straightforward, planning is critical to ensure the correct segments are peered and security tools are configured for consistent protection. Effective monitoring ensures that peered networks operate correctly and securely. Azure Network Watcher provides connection troubleshooters, packet capture, and next-hop analysis to verify routes. Metric data can be viewed in Azure Monitor, revealing usage patterns and potential bottlenecks. Logs, such as Azure Flow logs or diagnostic settings, grant visibility into traffic passing between peered VNets. Network administrators analyze these insights to detect unauthorized connections, verify network performance, or identify misconfigurations. By systematically capturing metrics and trace data, organizations can refine their peering architecture, address capacity constraints, and maintain compliance across interconnected cloud workloads. When connectivity issues arise, basic steps include verifying that the peering status is connected on both VNets and confirming address ranges do not overlap. Reviewing NSG rules is another key step. Misconfigured rules may inadvertently block traffic. If advanced routing through a virtual appliance is in play, confirm that Allow Forwarded Traffic is active. Network Watcher's Connection Troubleshoot feature can detect if packets are dropped or misrouted, while logs highlight relevant flow data. For cross-subscription or cross-tenant peering, check role assignments. Ensuring these facets align often resolves disruptions, restoring connectivity between peered networks. Peered VNets typically deliver high throughput and minimal latency by taking advantage of Azure's global backbone. Nonetheless, an organization's design choices can influence performance. For instance, traffic passing through a network virtual appliance may face additional constraints depending on appliance capacity or processes. Gateway transit also involves overhead, so verifying gateway SKUs and bandwidth limitations is prudent. If large volumes of data must move between regions, consider ExpressRoute or dedicated connections. By balancing cost and speed needs, administrators can design a peering strategy that satisfies application demands without introducing unnecessary complexity or latency to the architecture. In elaborate environments, multiple VNets may be peered in hub-spoke or full mesh topologies. A hub-spoke design dedicates one VNet, known as the hub, to shared services like firewalls, while spoke VNets host application-specific workloads. This pattern simplifies management and centralizes security. Full mesh configurations, in contrast, peer each VNet to every other, supporting diverse traffic flows. While flexible, mesh arrangements become more complex to govern. Some deployments merge peering with Azure Virtual WAN for extensive, globally distributed networks. Each pattern supports distinct strategies for scaling, security, and operational control, reflecting deeper capabilities of VNet peering. VNet peering proves beneficial for organizations hosting multi-component applications, such as web front ends, data services, and analytics clusters. A two-tier e-commerce site might store inventory and transactional data in a secure database VNet, while a front-end VNet boldly scales behind an Azure load balancer. The two VNets connect through peering, ensuring direct access without exposing data publicly. Integration across regions supports disaster recovery or cross-region replication in active-active scenarios. In hybrid setups, Gateway Transit extends on-premises connectivity to multiple Azure workloads. These patterns reveal the versatility of peering in supporting modern, dynamic cloud infrastructures. Implementing virtual network peering is most successful when grounded in well-structured address planning to prevent overlaps. Align peering decisions with organizational security standards, using NSGs or firewalls for traffic inspection as needed. In large-scale deployments, define consistent naming schemes for peerings to reduce confusion, especially when managing cross-subscription or cross-tenant links. Monitor network performance through Azure Monitor and gather logs with Network Watcher. Evaluate potential gateway transit usage to optimize resource costs and ensure role assignments are in place for multi-subscription collaboration. By focusing on these practices, administrators can build robust, scalable, and secure network topologies in Azure.